Okay, this is Chapter 9B, Lesson 1C. What I have written on the board here are 3 power series that we developed in previous sections. The first 3 were developed because they are sums of geometric. The fourth one, the sine of x, we raw constructed in section B, Lesson 1B that is. Each one of these has an interval of convergence, and the first one was from -1 to 1, as was the second one, as was this one. This one had an interval of convergence of all real numbers, so from -infinity to infinity. I want you to look at these. I want you to commit these to memory to some degree. Say, all right, the first 3 I could figure out geometric, but absolutely the sine of x, you need to commit that one to memory so I can illustrate the value of that. Okay, let's move on. Okay, in this first example, we're going to look at f of x equals 1 over the quantity 1 minus x squared, and we're going to come up with a power series. The idea here is we're going to manipulate one that we know, so I'm going to make a note down here. My note is, you may not recognize this, but with some practice you will, that this is actually the derivative of this other function, which we already know. Okay, I'm not sure how much I lost. It looks like I lost my audio, but we're going to look at the function f of x equals 1 over 1 minus x quantity squared. We're going to note that that function is actually the derivative of another function which we know its power series. So this then is going to equal the derivative with respect to x of the power series I showed at the beginning of the lesson, which is 1 plus x squared plus ... plus x to the n. And if we take the derivative term by term by term, we see the first one is going to be 0. The next derivative, which is the derivative of x, is 1. So derivative of the next term, 2x, plus the derivative of the next term, which is 3x squared, plus ... plus n, x to the n minus 1, plus ... and of course I need to ... up here. So what we've done is manipulate a known series to develop a new series. And this one, if we write the summation notation, we can say from 1 to infinity of n x to the n minus 1. Now, a note about the interval of convergence. The interval of convergence for this guy was from -1 to 1. By taking the derivative, you cannot add any points of convergence, so this interval of convergence will remain the same. And so this is going to be true for -1 less than x is less than 1. Okay, in the next one here, g of x equals the natural log of 1 plus x. And what we're going to say about this one, if I can find my cursor, what we're going to note about this one, is that the natural log of 1 plus x is actually the integral of 1 over 1 plus x. However, we're going to say from 0 to x, and we need a dummy variable, so 1 plus t dt. Okay? Because the natural log of 1 plus x is the integral of 1 over 1 plus x. Now, that means we're going to take the integral from 0 to x of these terms, which we showed in the beginning, which is 1 minus t plus t squared minus ... plus -1 to the n t to the n plus ... Now, I want to be careful with my notation, so I'm going to employ the fundamental theorem of calculus. First, I'm going to take the integral of each term, term by term. So this is t minus t squared over 2 plus t to the third over 3 minus dot 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 plus negative 1 to the n, t to the n plus 1 over n plus 1 plus dot dot dot. And we're going to take that from 0 to x. Okay, so doing that process, we're going to now plug in x for the t's. So we get x minus x squared over 2 plus x cubed over 3 minus dot 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 plus negative 1 to the n, x to the n plus 1 over n plus 1 plus dot dot dot. That's when we plug in x. But now when you plug in 0 to each one of these terms, those terms will each respectively go to 0, so that does not contribute anything to the series. So we have successfully come up with a power series for the natural log of 1 plus x. And in sigma notation, that is going to be negative 1 to the n, x to the n over n. A little sloppy getting crossed with the others. Perhaps I could write that more clear here. Again, that's the sum negative 1 to the n, x to the n over n, and that would be from 1 to infinity. It looks slightly different than the x plus 1. That could be said indexed at 0. So there's the power series. Now, a word about the interval of convergence. So the interval of convergence, negative 1 to 1, applied to this portion right here, that series. But when you integrate, you actually can add points of convergence. And through a ratio test, we would learn that this endpoint 1, it also converges at that endpoint 1. In the next example here, we're going to look at the function h of x equals the inverse tangent or arctangent of x. So this is the section where we are manipulating knowns. So we're going to note that the inverse tangent of x is the integral of 1 over 1 plus x squared dx, that you know. So we're going to say that the inverse tangent of x equals the integral, now I'm going to add bounds, 0 to x of 1 over 1 plus the dummy variable t squared dt. And again, we're going to now integrate, or substitute the terms of this series, which I wrote at the beginning of the lesson. So we have 1 minus t squared plus t to the 4th minus t to the 6th plus dot 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 plus negative 1 to the n, x to the 2n plus dot dot dot. Of course, I really should be careful here and say dt, and it also looks like I made a mistake here. That should be also a t. There we go. Okay, so now what I'm going to do is integrate term by term by term. So t minus t cubed over 3, not factorial now, plus t to the 4th over 4 minus dot dot dot. Let's see what the nth term, negative 1 to the n, t to the 2n plus 1 over 2n plus 1 and plus dot dot dot, and we will take that from 0 to x. Plug in x now and you get x minus x cubed over 3 plus x to the, I feel like I made a mistake. I did. This should be a 5. And this should be a 5. I forgot to integrate that. Okay, so x to the 5th over 5 minus ... plus -1 to the n x to the 2n plus 1 over 2n plus 1 plus ... We have to now plug in the 0, but you see again that that has no influence on the series. So this is what it's going to look like. Let's write the summation notation for the inverse tangent. So the summation notation for the inverse tangent, I'll leave that to you. It's also in the textbook. I want to talk about the interval of convergence, which initially was this, but remember through integration we could add points of convergence, and we would actually find through the ratio test that -1 and 1 are values that also make this series converge. For this final example, probably the most important, f of x equals the cosine of x. The reason this one is important, it's probably one that, well, I know it's one that you should memorize, but it's more the type that you'll see. So anyway, we're going to make a note that the cosine of x is related to something we already know. It's related to the sine of x, the derivative of the sine of x. So we want a series for the cosine of x. So cosine of x equals the derivative with respect to x of the sine of x, and you must have that committed to memory, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus ... plus -1 to the n x to the 2n plus 1 over 2n plus 1 factorial plus ... You might notice that that looks a lot like the inverse tangent, except the inverse tangent does not have factorials. Let's see. So what I'm going to do is take the derivative term by term by term. So we have 1 minus, now this is going to be 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus ... plus. I want you to see here that the 3 and a 3 factorial will cancel out a 3 and leave us with a 2 factorial. Likewise, the 5 will cancel out with the 5 here and leave us with 4 factorial. So what this is going to bring us to is x to the 2n, and then the 2n plus 1 will cancel out to leave us with 2n factorial plus ... Really important here. You can also develop this through raw construction, but after this lesson, you really shouldn't do either this manipulation or the raw construction. You should simply memorize that, memorize the series for the sine of x and the cosine of x. You should also memorize the series for e to the x and the inverse tangent of x. There will be one more lesson section of this entire lesson, and there we will show why it is important to have these memorized. Okay, hopefully you enjoyed, hopefully you understood, and hopefully the audio was not too bad. Goodbye.